Hey folks, how you doing? Going to finish up the review for the exam today. While we're here, let me just couple of reminders. On Wednesday, we will not be meeting in McBride. I will be available over Zoom. And if you want to come by during our meeting time over Zoom, you're welcome to. I'm happy to go over any kind of questions y'all have about the coding project or the test. Either way, either one of them. But don't show up in McBride on Wednesday because I won't be there. And let's go ahead and get started on this. We got through problems 1 through 10 last time. Let's take a look at number 11 here. How do Alice and Bob establish a shared private key over a dirty channel? We want to be ready to reproduce these steps in the Diffie-Hellman algorithm. So first step is that Alice or Bob, one of them, but Alice chooses a large prime number P and some number A, which is a primitive root Okay. We talked about primitive root last time, but a primitive root means that a to the first mod p, a to the second mod p, all the way up through a to the p minus 1 mod p are all different. The requirement that they all be different makes this harder to crack because we have p minus 1 different possibilities for the exponents instead of some smaller number of possibilities that just cycle around. So that's the requirement for taking a primitive root here. She sends these to Bob. A and P to Bob. So now these two values are compromised because our channel is dirty. Alice and Bob each choose a private exponent. So Alice chooses an integer j, and Bob chooses an integer k. Alice sends Bob a to the j power. Bob sends Alice a to the k power. And now these values are also dirty. I'll circle all of the dirty values here. So this is where the discrete log problem comes in. If we know A and P, we can compute A to the J computing A to the J is O of log A. But figuring out what J is O of 2 to the A. Or not A, P, O of log P and O of 2 to the P. And so if P is we want P to be in a sort of a zone where O to the log P is doable, but O to the 2 to the P is not doable. And so we need to choose a large P to be able to do this. Otherwise, whoever is observing our channel could, figure out what J is by brute force, and we don't want that to happen. All right. So now that this is done, Bob and Alice takes Bob's dirty value, a to the k, and raises it to the j, computes a to the k raised to the j power, and Bob computes a to the j power to the k power. And these are the same, of course. Actually, we have to compute these mod p, because they might not exactly be the same, but they'll be the same mod p anyway. And this will be our shared value. And again, it remains secret as long as our attacker can't extract the values of j and k, because that value is too difficult to extract based on the value of p. Okay? So that's the Diffie-Hellman algorithm. All right, define the function phi of n. So here's the definition. Let n greater than 1 be a positive integer. Then phi of n is the number of integers 1 less than k less than n, which are relatively prime. For example, we look at phi of 24. We think of all of the integers that are up to 24. And then think of ones that are relatively prime to 24. Well, any even number won't be relatively prime to 24, because any even number has a common factor of 2. So I'll cross out all of the even numbers. And any multiple of 3 will have a 3 in common. So 3, 6, 9, 12, 15, 18, 21, and 4. The remaining numbers here are all relatively prime to 24. And how many are there? There are a total of 1, 2, 3, 4, 5, 6, 7, 8 of those. And so phi of 24 is equal to 8. All right. So that's how we compute phi of n for a relatively small integer. If p and q are both prime, what are the values of phi of p times q? Okay, so there are a total of p, q integers in the range 1 less than k less than pq. Q of them are multiples of p, and p of them are multiples of q. Q of them are multiples of phi. In fact, they are 1 times p, 2 times p, 3 times p, all the way up through q times p, which is our value pq. And p of them are multiples of q. And they are 1 times q, 2 times q, 3 times q, all the way up through e times q. And again, so these are not relatively prime, and these are not relatively prime. To PQ. But one value is in both lists. PQ is in both lists. But PQ got counted twice. And so what we get is PQ, the total number of integers, minus Q plus P, the ones that are not relatively prime, plus the one we undercounted. Correction for overcounting. We're really using the inclusion-exclusion principle here, that we are including both of these, but then because there's one shared value, we have to exclude it from being counted twice. So that's the same as PQ minus Q minus P plus 1. Okay. All right. So even so for a small integer, we can calculate phi of that small integer pretty quickly. If we choose two large prime numbers, we can calculate phi of that product quickly because we have a trick for it. Okay. All right. So let's state the Euler-Fermat theorem. The Euler-Fermat theorem says that if the GCD of A and N equals 1, then A raised to the phi of N is congruent to 1 mod N. Okay. Okay. So this is all this says here. So example, we've already seen that phi of 24 is equal to 8. And we know that the GCD of 5 and 24 is equal to 1. And so we can conclude that 5 to the 8th power is congruent to 1 mod 24. Without actually having to work this out, we could, but we'd be okay. And it's actually pretty easy to see why. 5 to the 2nd power is 25, and 25 is congruent to 1 mod 24. And so, well, I can say that 5 to the 2nd power is 25, which is congruent to 1 mod 24. And so 5 to the 2nd power cubed is congruent to 1 cubed, which is congruent to 1 mod 4. And so 5 to the 8th is congruent to 1 mod 24 if we actually work this out. But we didn't actually have to work this out. We knew this as a fact because 5 raised to the phi of 24 is always congruent to 1 mod 24. All right. So this is the Euler-Fermat theorem, that A raised to the phi of N is congruent to 1. So how does RSA make use of the Euler-Fermat theorem? Okay. So Alice chooses two large values, P and Q. Okay. She computes phi of P and Q, and not phi of P of Q, phi of P times Q. Go. So she computes phi of Q, and then chooses a base. Actually, she chooses an exponent. And exponent E, which is relatively prime, to um, to PQ here. Um, all right. So what does she publish? She sends Bob the values of E and the value of N, which is PQ. Okay. We want this number to be hard to factor. Because if P and Q were small enough that we could factor in quickly, then anybody observing the channel could then figure out, if they knew what PQ was, they could compute phi of PQ pretty easily. And we want that value to be secret. All right. So then Bob takes his message M and raises it to the E power N. So Bob sends Alice M to the E power mod N. Okay. So again, this operation of figuring out M to the E power is O log N. But figuring out what E is O of 2 to the N. And so we don't want this to happen. So we don't want an attacker to be able to figure out what E was, because otherwise they would have some secret information here. So sorry, not extracting E, extracting M, figuring out what the base is. E is public. Extracting M from this information is O of 2 to. All right. So now what Alice is going to do is compute E inverse mod phi of PQ. So phi of PQ is still secret. Again, I'll circle the dirty values in red. E is dirty, N is dirty, M raised to the E power is dirty. But this value here is not dirty yet. And it won't be dirty if N can't be factored. And so that value here is still clean. All right, so let's call this value D. So then Alice computes M raised to the D times E, which is congruent to M to the 1, because D times E is congruent to 1 mod PQ, and that's just congruent to the message. And so that's how Alice is able to read the message, is by using the Euclidean algorithm here to compute this multiplicative inverse. Okay. So how does RSA make use of the Fermat theorem? Is right here at this very last step. If it says DE is congruent to 1 mod PQ, let me just come up here and make a little more space, then DE is actually equal to some multiple of phi of PQ plus 1. That's what it means to be congruent to 1 mod PQ, is it's not actually equal to 1, it's equal to a multiple of PQ plus 1. And so M raised to DE power is the same thing as M raised to the K times phi of PQ plus 1, which is M raised to the phi Q, PQ raised to the K power times M to the first. But this is where Euler-Fermat comes in. This is equal to 1 to the K, and that's where things happen. So 1 to the K times M. That's why that is equal to just M down here. The Euler-Fermat theorem comes in the very last step, is why Alice is able to get your M back. Okay. All right, 2 more questions. Let's get through them. Pollard P-1 factorization. If we're given a bound B, how do we find the exponents used in the factorization attempt? Bear with me. My allergies are bad this morning. So let's look at an example. Let's say we have a B value of 18. We first list all of the prime numbers up to 18. So primes less or equal to 18 are 2, 3, 5, 7, 11, 13, and 17. And then we look at the largest primes that we can pick, or the largest powers of primes that we can pick that are less than 18. So this is going to be, so the highest power of 2 is 2 to the 4th, which is 16. 3, I can just go 3 squared. 3 squared would be 9. 3 cubed is 27, and that's too big for 18. And then anything else, if we square them, they're bigger than 18. So every other value, their highest power is just the first. And so if we choose B equals 18, we would get these exponents right here. Or in order, I would put them as 5, 7, 9, 11, 13, 16, and 17. Okay. So that's how we would choose the exponents that we would use. What we would then choose is we would compute for each of these powers. We would attempt to compute the GCD of 2 to the k minus 1 mod p, NP. Okay. So, and look for some value in this list that's not equal to 1. Okay. We'll try an example in the next page. Okay. All right. So this is number 16. Go ahead and factor a reasonably small integer using this technique. So what we're going to factor is the number 95 using e equals to 4. So for 4, we only have 2 primes. We have 2 squared is less than or equal to 4, and 3 to the first is less than or equal to 4. So my exponents are 3 and 4. And so what we'll do is we're going to calculate 2 cubed minus 1 mod 95 and 2 to the fourth minus 1 mod 95. Well, 2 cubed minus 1 is just 8 minus 1, which is 7. So 2 to the fourth minus 1 is 16 minus 1, which is 15. And now what we would like to do is find the GCD of 7 and 95 and the GCD of 15 and 95. And the GCD of 7 and 95 is 1. That's no help. But the GCD of 15 and 95 is 5. And so 5 divides 95, and 95 divided by 15 is 19. Well, those are my 2 factors. So 95 is equal to 5 times 19. Okay. This was a small enough integer we could have figured that out in our head maybe a little faster. But the idea here is that that I set a boundary of 4, but I actually yielded an answer that was bigger than my boundary. If we're talking about a very large value of n, the ability to search through a limited range, but still have a chance of being able to find factors that are outside that range, improve the chances of being able to find factors of this, because brute force searching would be even slower. All right. So, like I said, Wednesday, show up on Zoom if you've got questions. I'll be on Zoom from our regular class time, which is 11:15 to 12:05. And then the exam will open Thursday morning and will be open till Friday evening. You'll have an extra day to schedule this so that you can enjoy your 3-day weekend. All right. Now take care.